So we've spent the first half of the year learning how to take the derivative or differentiate a function or series of functions, and now we're actually going to go backwards and take what's called the indefinite or definite integral, which is also known as the antiderivative. So by definition, we have a function f, capital F, is called an antiderivative of a function, lowercase, this is just to distinguish between the two, on a given open interval if capital F prime of x is equal to f of x for all values on that interval. So given this theorem, if capital F of x is any antiderivative or integral of f of x on an open interval, then for any constant c of this given function, f of x plus c is also the antiderivative. Basically what this is saying is when you differentiate a function, let's say a polynomial that has a constant on the end, the derivative of that constant is 0. So you need to accommodate for that when you're taking an indefinite integral. And we'll get into definite integrals when you actually find the specific c value later. But for an indefinite integral, meaning you have no bounds, you must include a plus capital C to accommodate for the fact that there could be some kind of constant value. Okay. So the indefinite integral here, the process of finding the antiderivative is called antidifferentiation or integration. I prefer integration because antidifferentiation is just a mouthful. So this notation here, d dx of capital F of x is equal to f of x. So integrating this function produces an antiderivative of the given form, capital F of x plus c. So they're saying that you're going backwards to the original and there could be some constant on the end. And you can also use what's known as integral notation. So this right here, you need to know is an integral. Okay, you're going to see it a lot, and it means to take the antiderivative, or basically go back to the original function, and this would give us capital F of x plus c. Okay, and again, where c is understood to represent any arbitrary constant value. It could be anything. So it's also important to note that there are two different types of notations, and as I showed you before, and I'll show you how to do this, here this is saying if you take the derivative of 1/3 x plus, 1/3 x cubed plus c, you get x squared, because here when you take the derivative, you end up with x squared, and the constant, which could be 7, 12, negative 13, 8, whatever it would be, becomes 0. Here, they're saying that you're going backwards. We're going from the derivative to the original function. So some important notations to understand. The adjective indefinite emphasizes that this is just a generic function. You have no bounds. So you just have to accommodate for the fact that there could be a constant with this generic notation. The elongated s is known as the integral sign, like this. Okay, and the function f of x is known as the integrand. So think about it like this. If you have a radical, what's underneath is the radicand. It's the same idea. The c is the constant of integration. And what happens most often is that people forget the plus c, and it will cost you. So what you just need to understand is that this could be any notation. The integral of s of t dt is capital S of t. Here you have h of theta d theta, or g of u du. The variables do not matter. It's the notation and the understanding that it means the same thing. In addition to that, if you think about some of the notations that we write, for example, if we write the variable x, a coefficient of 1 is implied, an exponent of 1 is implied. Therefore, if you are integrating 1 dx, meaning this is just a 1 here, a lot of times you're going to see the integral of dx, and you need to know that the implication is that there is a 1 in front. Therefore, when you integrate this, the variable would be x. In addition to that, this right here, this notation means 1 over x squared times dx essentially. So a lot of times you're going to see it written like this. you need to understand that these aren't interchangeable. Oftentimes you will see the second notation because it is shorter, and the whole purpose is to create a smaller, tighter function that looks neater. Okay, so here we have a series of differentiation formulas. These are all the derivatives that you should have learned. They were in your concept cards. Same thing here. Now we need to go backwards. So these are all our integral functions. Okay, so here I'm saying to take the derivative of x, I get 1. To integrate dx, which is the same thing, this is x plus c. So all of these that I've highlighted are in your concept cards, and I highly recommend that you go back and take a look at these. The other way you could do it is with the flashcards. If you have any, go backwards. The last one that I just want to note is this last one right here is rarely ever seen. I did highlight it because it is one of our inverse trigs, but most often you just saw inverse tangent, inverse sine. We don't really ever do inverse secant. Okay, so for the last piece, we're going to cover just a couple theorems, definitions. So what we have here is a theorem that states that we have two functions, f of x and g of x, and they are stated to be the antiderivatives of f of x and g of x. So capital F, capital G, okay, antiderivatives. So these are the original functions. These would be the derivatives, and c is a constant value. So if you have a constant factor, just like when we would take the derivative of something like 2x squared, this is just a coefficient. It's just hanging out there. So what they're saying here is, if you integrate this, another way you can think about this is your constant or your coefficient is going to be on the outside. You would integrate the function itself, and then when you finish, you would multiply whatever that coefficient is times the antiderivative, okay, plus the constant. All right, so that's just one way to think about it. These two are very much the same, so I'll just talk about them together. Here you have an antiderivative of a sum and a difference. If you have two functions that are being added together and you are integrating them, you can integrate them individually, meaning you would integrate the positive or the negative f of x dx, and then either add or subtract the integral, depending on what you have here, of g of x dx. So you can do them separately if you can't combine anything, and then combine your like terms at the end.